Hi everyone. Today I wanted to bring another statics problem. More specifically, I wanted to introduce you to some of the concepts of frames of machines. And this problem in particular is very interesting, and you see in a little bit, because it has an interesting geometry going on. And I wouldn't say it's hard, but definitely not a trivial problem. Um, so let's just get to it, right? So the problem says determine force P on the cable if the spring is compressed 0.025 meters when the mechanism is in the position shown. The spring has a stiffness of 6 kilonewtons per meter. Okay, so before we get to it, let's just draw a free body diagram. And I'm going to try to cheat a little bit and draw on top of it, which I don't recommend that you do. And then I'll just remove the picture in a bit. Drawing this free body diagram real quick. And I'm going to try to catch some of those measurements. This is 0.2. This is 0.8. This is 0.15, 0.2, and lastly 0.2. And obviously, well, I should probably draw that dashed. 30. Okay. So let's see. If I move this around, alright, cool. Let's see. So with my free body diagram, I just wanted to do that. And this is obviously A, B, C, D, and obviously E. That was F. We have a force being applied by the spring. To determine the direction of the force, which matters a lot, because it could be in tension or compression, we should do this, right? Think of Newton's third law, and this spring is being compressed. So the mechanism is pushing on the spring, which means that the spring is pushing back down. So that's how you figure out that direction. And by how much? We get that F equals 6,000 if we convert it times that delta X, how much the spring was compressed, 0.25, 0.025 I should say. Oops, let me try to drag this a little bit more. 0.025, and I believe this is 150. Let me double check. Yep, 150 newtons. Okay, so now that we have that, we can start to worry about the reactions, right? So I should have drawn this as AX, or maybe I should change colors, right? That would be awesome. Better for visualizing. So this is AX, this is AY, this BX, this is BY, right? So those are the only pins that mechanism has, and it looks like that's about what we can do with the general free body diagram before we have to break it up. Okay, so a good procedure for those type of problems is try to see if you can gather some information from the general free body diagram before you break the mechanism apart. Okay, in this case I already know um, what the correct procedure is to solve this problem, because I already attempted it this time and made a small mistake, even though the procedure was right when I was, making this video, obviously. So I already know the shortcuts to this problem. I didn't when I first tried it. Yeah, my first recording didn't go well. Made a small math mistake. But what I'm going to do is purposely do something, and I'll explain why I did it purposely, okay? So I'm going to do some of the moments about B. And that's kind of like the thing that I'll be doing on purpose. And when I do that, actually, let me think about this. I don't think I can do that. And I can't do that because I don't have this distance here. And there's no way through the geometry that I can figure it out. Okay? So that distance is not given, which doesn't allow me to calculate the moment that the force AY causes about point B. So, and also, yeah. So I can't get this distance here. Okay? So it looks like I'm just gonna have to tell you what happens with this problem. So the issue that I also had when I first attempted it, and I recognized it halfway when I was doing it, is that since we don't have this distance x, we can't really get valuable information from this free body diagram. The only thing we can come up with is some of the forces in the x and some of the forces in the y. Okay? And remember, here we have 5 unknowns, and technically we could use 3 equations, some of the forces, some of the moments. But like I said, I can't do the sum of the moments about B or about A or any other point because I don't have this distance x, right? That's very valuable. For any other point I pick, I need to get that distance. So I'm just going to move on, and then we'll come back and fix this free body diagram to make it easier on us. So before I fix it, I just want to, kind of walk you through breaking the mechanism apart. So first thing we should do is we recognize the links. So this is one link. Okay, I'm drawing it on the picture. It's a rigid body on its own. Okay, and the way you recognize it, you just look at the assembly and you see that it's not split. So the drawing itself doesn't show any superposition of lines. So for instance, by superposition, like this line is a superposition, so it means that it's a different link. Okay, and this line is also superposition, so that's another link. So really this is a link on its own. So from A to F, that's a link on its own. Okay, so link AF, keep drawing the same direction, so AX, and let me just erase this guy here to the right, and AY to agree with my general free body. Consistency, very important. Then, because I'm only drawing that link, I'm taking the pins apart, so I'm going to get a pin reaction there, which I'm arbitrarily drawing that way. CX and CY at point CE, where the pin was, and obviously the external force, 150. And that's it for this link. Okay, those are the only pins that are attached to that link. So through this link we can get some information for sure. We won't be able to solve those. So 3 equations, we can use 3 equations, right? So let's start with sum of the forces in the x equals 0, positive to the right. Okay, then we get ax plus cx equals 0. Cool, so that's one equation. Sum of the forces in the y equals 0, positive up. We get cy is equals to 150. Oh, sorry. cy plus ay. Okay, that's another equation. Doesn't really help us much right now. And then some of the moments, I'll just do it about A. What do we get from here? We get that Cx and Cy cause a moment. So Cx is going to want to try to rotate our mechanism clockwise. So negative Cx. Perpendicular distance is 0.2. And then Cy is going to try to rotate the mechanism counterclockwise, so positive. About A is going to try to rotate us counterclockwise, so Cy times also 0.2. And then obviously 150 is going to want to rotate us clockwise, so negative 150 times the distance of 1 equals 0. Okay, so we have 4 unknowns, 3 equations, definitely not enough to solve anything. Okay, so let's just jump to another link and see what happens from there. So the other link that I'm interested in is this link EDC. So link EDC, I guess I'll draw it right here. Let me just keep it in blue for consistency, right? I'll put the forces in black. Okay, so we have the force P, which is our unknown, what we're looking for. Then we have Cx and Cy. And notice that I'm drawing them in opposite directions on purpose. It's a pin. We're taking it apart. By Newton's third law, we need to do it that way, otherwise it would be incorrect. Okay? So every time you take it apart, if it's a different link, you invert the directions, right? So when I do some of the forces and some of the moments, those are gonna change from link to link, right? You're gonna have to respect those directions. Anyways, so the only missing piece is the force at pin D, right? The interesting thing about this problem is that link BD is considered a two-force member. So if you remember from trusses, the property of two-force member, or the characteristics, is that the force goes right through the member. So it's an axial, it acts as an axial load, which means that we don't have to draw it as, for instance, I'll erase it, dx and dy. We already know that that force is either going this way, or I could choose, right, this way. Okay, we don't know if it's in tension or compression. We tend to draw it in tension just because that's kind of the norm, right? So I'll keep it like that. And this is 30 degrees, and I'll call this FBD. Okay, and that's kind of the key to solving this problem, is recognizing that as a two-force member, because if you recall, I was struggling in the beginning. If I do that, it means that BX and BY are no longer two components separate. I mean, I will already know the direction that the reaction is going. It's going in the BD direction. So there's no need to draw two components. Even though you can still split them into components, you already know the direction. Okay? So that said, I can actually erase this whole link here. Okay? And I can draw this as a kind of like a support reaction, FBD. And that solves my geometry issues that I was having. Because before, I needed a distance x to calculate the sum of the moments, and now I don't need it anymore. So if I do sum of the moments about A, like I was first trying to do at the very beginning of this video, I won't need this distance x. Look, FBD is also acting at D just like it's acting at B. It's the same two-force member that's going through those 2 points. So that force can be just considered to be transferring over from one point to the other, right? And since we're not concerned with link BD, we don't have to worry about it for the general assembly of the mechanism. We can analyze it the way I have it now. And with that said, literally all we have to do is just account for the two components of FBD and use the 0.2 distance that was already given to calculate the moment that at first was not possible to calculate because we didn't have the distance x. Okay? So let's just do it. So sum of the moments about A. Let me erase these guys here because I think I'll need some of that space. Equals 0. We get that FBD, FBD, let's start with the x component, right? The x component is going this way. It's going to want to rotate the mechanism or about point A in the clockwise, so minus clockwise direction. So minus FBD, and that was sine 30, correct? And then the other component was the y component going down. Oh, I forgot the distance, my bad. So that distance was 0.4, 0.4. The other component was the cosine, so FBD cosine 30. And that distance, let me just drag this real quick to the side. That distance was 0.2. Okay. And is it positive or negative? We're rotating, that force wants to rotate about A in the clockwise, sorry. So minus. And then we get, obviously, F, which was calculated as 150, rotating us counterclockwise, clockwise, sorry, I don't know what I'm saying, counterclockwise. So minus 150 times that distance of 1 equals 0. Oh, I did miss one more, which is P, right when I was checking. So we accounted for these two for F and then P, obviously. Same thing, clockwise minus P times the distance of 0.55, and now equals to 0. So it turns out that with this equation and one more equation, we can actually solve, right? So this kind of work here, even though it's very valuable for other types of questions, it doesn't actually need to be done, right? I didn't have to analyze this mechanism, this link, but I figured I'd go through it just to get to the point that I was trying to come across. Okay, so I could do some of the forces in the x, some of the forces in the y, in the overall assembly, but I'm choosing not to do so because I already know the path. Like I said, I already went through this problem. And even though I did the right procedure, I got the wrong answer, so I wanted to redo it for you guys. So the only other equation that we're going to need, if you notice, here we have two unknowns, right? So if we can find another equation with the same two unknowns, we're good to go. So looking at this first link here, there's no equation that has the same two unknowns. So we have to look at this other guy here, this other link, and see if we can figure out an equation. So if we do some of the forces in the x, Cx is going to pop up, and FBD and P are going to pop up. I'm going to add another unknown if I do some of the forces in the x, so that's not going to be helpful. Cy is going to be added as an unknown if I do some of the forces in the y, and I don't want that. I'm not interested in finding Cy. So my last option is to do some of the moments about C out of convenience, because then I can just, Cy and Cx are going to be eliminated because they don't cause a moment about C. If I do that, FBD and P are going to pop up, and I'll get my two equations, my second equation for my two equations, two unknowns, goal, right? Which is to then solve and find P. So let's do that. So if we do that, the component, the x component of FBD is the only one causing a moment about C because it's the only one that has a perpendicular distance to point C. So, and that is trying to rotate us negative, so clockwise, so minus FBD. and this one was also sine of 30, and the distance is 0.2. Okay, and then p was a distance away of 0.35, so minus p 0.35 equals to 0. So this is my other equation. And then if I solve in my calculator, I'm just gonna do a solver here, system of equations solver 2 by 2 to get to the answer, because that's just, algebra. Let me see what I get for us. Let me see. So I should probably condense these a little bit, but I can do that on the calculator. If I condense those, let me see, I have p right here. Then I have, so I'm going to be doing sine 30 times 0.4 plus cosine 30 times 0.2, right? And then that looks correct. And then the other guy was sine 30 times 0.2. Yep, that looks correct. So it turns out that P was calculated to be 198.3. And I'll just give it to you as well. So FBD was calculated as negative 694.24. Okay? So let me just highlight all these guys so you have the full answer. Okay, and then we'll do a quick recap on the discussion here to try to explain what was going on. So that's the answer, and just a quick recap before I go. I wanted to say that this problem, right, even though it looks kind of challenging at first, once you go through it and once you take it apart, you should be able to identify, or at least at some point you will identify, that this link BD, being a two-force member, is what's going to allow you to solve this problem. If you don't identify that from the beginning, like I didn't before when I did it at first time, at my first attempt, it's okay, because at some point when you break it apart, you notice that it's a two-force member. By noticing that, you should quickly go back and fix it wherever you put it as not a two-force member, right? So for instance, before I had this split up, right, in two components. That's not incorrect, but that's just going to add one more unknown that will not allow you to solve this problem. So that becomes an issue, right? So once you realize that, you actually recognize that all you're going to need now is just one more equation. So breaking these links apart, I mean, the first one was completely unnecessary, and the second one was the one that we needed, right? So a lot of times in these problems, it helps to break it all apart, but sometimes if you do know what you're looking for and you have enough practice, you can just go straight to the link that you're interested in. But a lot of times it actually is not that helpful, because what you need is part of another link, and you need the solutions from that other link in order to solve. Now this problem in particular, it didn't really force us to do that. And for those reasons, I'm going to find another machine or a frame problem to try to show you how sometimes you need to solve link by link in order to get to the final answer, right? And the last thing I wanted to mention is, every time that you go through these problems, the main assembly, with the main assembly, you're able to get three equations out of it. So you could do sum of the force in the x, sum of the forces in the y, and sum of the moments about some point in the mechanism, right? When you break it apart into separate links, you get three other equations, the same ones: sum of the forces in the x, in the y, and sum of the moments about a point, right? So be smart about which ones you're using, because you don't necessarily have to write all of them. And you know, if you do happen to solve for more unknowns that you needed to, that's not a problem. At some point you get enough practice to where you can just focus on what you need. Okay, but like I said, this is kind of a unique problem. It required the two force member understanding, and that's why I think this was a cool problem to solve. Okay, so that's it. I'll post another one, and if you like this one, just let me know. And as always, please let me know if you have any suggestions or any questions. Take care. Bye bye.